Welcome back. In the last video, we explored 284,807 credit card transactions and discovered we are dealing with extreme imbalance, only 0.17% fraud. Today, we are building our first machine learning models. We will start with simple baselines, then try different approaches to handle class imbalance. By the end, we will have multiple models trained and compared, and we will see which one performs best. Let's jump right in. So first, let's import our libraries to set up the environment. I'm importing pandas and numpy for data handling, matplotlib, and seaborn for visualizations. Then a bunch of scikit-learn tools. We will need a train task split for splitting data, um, standard scaler for scaling features, and several different algorithms like logistic regression, random forest classifier, MLP classifier for neural networks. I'm also importing imbalanced learn library, which has SMOTE for handling class imbalance, and Jopley for save our trained models at the end. So you can see the library imported successfully. Notice it is printing the current timestamp because it's useful for tracking when models were trained. So now let's load the data. I loaded the credit card CSV file and checking the basic info, like what's the total number of transactions, how many features. So you can see we have 284,807 transactions, 31 features, 492 frauds, same data as we explored last time. Now here is something new, feature engineering. I'm creating some new features. So you see here have amount log. Um, it's a log transformation of amount. So it will help with the skewed distribution we saw from earlier. Also, I'm creating a new feature called hour, extracting the hour of the day from time. And then the time-based feature like time sin, time cosine, is just encoding the time because hour 23, hour 0 are actually close together. So those engineered features can help models learn time patterns better. So now we prepare the other features. I'm selecting all columns except the class and time as features. So I have 28 features amount and my 4 new engineered feature. So should be 33 total features. Then I'm split into training and test with an 80-20 split. I'm using the stratify equal y. This ensures both train and test have the same 0.17% fraud rate. This is very important and beginners often forget this step. I'm using standard scaler to standardize all features to have a mean of 0 and standard deviation of 1. Because our features have a very different scales. Time goes up to like 170,000 seconds, while V features are around -5 to 5. Without scaling, some algorithms would be dominated by the large scale features. So I feed the scaler on training day only, then transform both train and test. This prevents like data leakage. We don't let information from the test set influence our processing. Look at this before and after scaling visualization. Before scaling, among has completely different skill than V1 and V2. And then after scaling, they're all like comparable. This mean is essentially zero, and the standard deviation is one across all features. Now we're gonna build our baseline model. So I'm basically using the class weight balanced. This automatic adjusts the weights to account for the imbalance. It makes the algorithm pay more attention to the real fraud cases, like class. Because we have class 0 and 1 as our target value. So after the training done, you can see for the logistic regression, we have a precision 0.0577. It's very low, so that means a lot of false positive. And the recall is 0.92. It's very high, so it means catching 91.84% of fraud. The F1 score is 0.11. It's very low because the precision is very bad. So the ROC and AUC is 0.97. It's very high, so good at ranking fraudulent transactions. So this shows like classic trade-off, right? High recall means catching most frauds, but low precision means lots of false alarms. Now let's look at the random forest. Random forest is an ensemble of decision trees. So I'm using 100 trees with balanced class weights and all CPU cores for speed. If you have GPU, feel free to use your GPU. Well, look at those numbers. So we have a 96%, 0.96 precision. So that means 96% flag the transactions are actual frauds. The recall is 0.76. So we mean catching 76.5% of fraud, and with 0.85 F1 score. So this is good because and 0.95 ROC-AUC accident discrimination. So random forest is dramatically better than logistic regression. This precision is high, like 96%. That means very few false alarms. So now let's try neural network. I'm using MLP classifier with two hidden layers, 100 neurons, then 50 neurons. So I enabled early stopping as well, so it stops training when validation perform um, good. So this is the results. Um, 0.89 precision, 0.73 recall, zero point 0.8 F1 score, 0.97 highest so far for the ROC. So good performance, but random forest still winning on the F1 score. It's 85. This is 80. So at end of this cell, it shows like a summary table capturing all those three baseline models. Random forest clearly it performs the best. So now let's look at the anomaly detection approaches. So this is a different approach. Instead of learning like fraud is normal, anomaly detection is what normal looks like. So anything unusual is flagged as a potential fraud. So I'm training isolation forest on only the normal transactions. So it learns normal patterns, then anything that doesn't fit the pattern is considered any anomaly. So I set the contamination of 0.002, expecting about 2% of test data to be anomalies. So after you run run the cell, you can see the isolation forest results. So we have a precision 0.17 and then 0.24 recall, 0.2 F1 score, 0.95 as ROC. So the ROC-AUC is good, but the precision and recall it's are lower than our supervised model, like random forest, not just regression. So anomaly detection, no, isn't the best approach here, but it could be useful in any ensemble. Um, Now let's look at the handling imbalanced class with SMOTE. So it's type of open sampling technique. So um, let's look at the we originally have a training data set. I had 227,845 samples with only 394 frauds. So the visualization shows the dramatic change in class distribution. So this is the original training set, and this is after SMOTE. So now let's first we use a random forest with SMOTE data. So you see I call the random forest classifier with the SMOTE data set. So let's see how the model performs. So we have recall 0.89 for precision, 80 for recall, 0.85 for F1 score. Um, it's interesting because the recall improved from 90, I think it's 76 to 80 percent, but precision dropped slightly. The F1 score it's about the same. And then the logistic regression with SMOTE, it's very similar to the class we did version. So SMOTE didn't help with logistic regression much. So now let's compare the model. So I'm creating a data frame with all models results sorted by F1 score, then creating 4 different kind of visualization showing different aspects. So let's look at those comparison. So first is you see the summary table for different cross different models, like class weighted versus small, and then precision recall F1 are seeing here. The first graph is the F1 score bar chart. So you can see the random forest clear performs the best. Then the second graph is precision with a record. It shows the trade-off. Like logistic regression has higher recall, yeah, high recall, and but very low precision here. So the third one is the ROC-AUC bar chart. So most models are above 0.95, so it's very good. And then let's look the heat map shows like all metrics for all models at once. So by looking at those graphs, I will see the best model by F1 score is random forest with 0.85. This is our winner with the SMOTE here. So it balanced precision and recall well, um, catching like 70, it's catching 76 of fraud with 96% of precision. Um, so the best model is random forest. So I'm creating full detailed visualization for our best model. So to show the comparison better. So look at the confusion matrix. It should show true negative, false positive, false negative, and true positive. And then ROC curve. So AUC is 0.953, excellent discrimination, and then precision recall curve. So we have average the precision 0.863, and then also show the top 10 feature importance, show which features random forest use most. So look at the feature importance. V14 is by far the most important. Remember from our exploration, it had the highest factor size. So V12, V4, V10 also very important. So the engineered features we created show up too. So the classification report shows a detailed precision recall F1 for both cases, both class. So, so this is where machine learning means business reality. So I'm basically calculating like how much fraud we prevented. I investigate costs from false positives, fraud losses from missed fraud, and net benefits. So the model caught 75 out of 98 frauds in the test data sets. So that's a 76.5% detection rate. So the financial breakdown shows fraud prevented value minus costs. And you can see the pie chart. It shows that what percentage of a fraud was caught versus missed. So we missed 23.5%. Now we're gonna save our models. So I'm saving all trained models, um, and the results and the best model separately. So also creating a model summary with the metadata. So after that, all saved, so we can load those models later for API or dashboards. So let's summarize what we have learned today. So we looked at class imbalance, and then different approach. And then we found out the random forest one with the 85% F1 score, 96 precision, 76% recall. Also, we looked the business impact, why it matters, because the high precision means a few wasted investigations. So in the next video, we will explore enhanced models like XGBoost and NightGBM, deep learning with autoencoders, graph neural networks, and sample methods. So currently our best is 85% F1 score. Can we do better? Let's find out in the next video.